Hi friends, I would like to discussing about Laplace transform of some standard functions. Okay, so Laplace transformations of some standard functions. Standard functions. Some standard functions. So first one, Laplace of t power n. So Laplace of t power n is equal to gamma of n plus 1 by s to the power of n plus 1, where n is greater than minus 1, s is positive. Okay, where n is greater than minus 1 and s is positive. So now we have to prove this formula. Okay, now from the definition of Laplace transform, from the definition of Laplace transform, so we have Laplace of f of t is equal to integral 0 to infinity e power minus st f of t dt. Okay, so Laplace of f of t is equal to integral 0 to infinity e power minus st f of t dt. Now here f of t is equal t power n. So now applying for this one, f of t is equal t power n integral 0 to infinity e power minus st t power n dt. Okay, now we have to evaluate this integral value. Now putting st is equal some z. Okay, so here s is the parameter, so z is a function of t. Now differentiate with respect to z is a function of t, so differentiate with respect to t on both sides. S into dt is equal dz. Now evaluating dt, so dz by s. So now replacing dz is equal dt is equal dz by s. And also what about t? Then t is equal z by s. Okay, now we have to calculate the limits for z. So if t is equal lower limit, t is equal 0, then what about z limits? Z is equal 0 times of s, 0. Next, upper limit, if t tending to infinity, then z tending to infinity, because so s infinity times of s, z tending to, as t tending to infinity, so then z tending to infinity. So the limits are z is equal 0 to z is equal infinity. Okay, now the given the above integral becomes integral 0 to infinity e power minus st t power n dt is equal to integral 0 to infinity e power, what about st, minus z, t means z by s whole to the power of n, dt means what about dt, dz by s. Now simplifying this integrand, so here z power n by s to the power of n, so s power n into s 1 by s to the power of n plus 1. So total this term is taking out integral 0 to infinity e power minus z power n dz. Okay, now again this can be written as 1 by s to the power of n plus 1 integral 0 to infinity e power minus z to the power of n plus 1 minus 1 dz. So since from the definition of gamma of n, since gamma of n is equal to integral 0 to infinity e power minus x to the power of n minus 1 dx. Now using this definition, so this can be written as gamma of n plus 1. So 1 by s to the power of n plus 1 times gamma of n plus 1. So Laplace of t power n is equal to 1 by s to the power of n plus 1 gamma of n plus 1. So here n plus 1 is greater than 0. That is n is greater than minus 1, s is greater than 0. So if n is any positive integer, gamma of n plus 1 is equal n factorial. Okay. If n is equal 0, 1, 2, 3 and so on in this above expression, so gamma of n plus 1 is equal to n factorial. Therefore Laplace transform of t power n is equal to n factorial by s to the power of n plus 1. Second one. Second standard function is Laplace of e power at. Laplace of e power at. So again from this definition of Laplace of f of t, so integral 0 to infinity e power minus st. So f of t means e power at dt. Okay. Integral this can be written as integral 0 to infinity e power minus of s minus a into t dt. So now applying this integral value e power of minus of s minus a t by n derivative is minus of s minus a. So 0 to infinity. Now we have to apply these limits. So here 1 by a minus s is constant. Okay. So limit upper limit as t tending to infinity e power minus of s minus a times t minus as lower limit t is equal to 0, e power 0 is 1. So as t tending to infinity, so here s minus a is positive. So now this condition is s is greater than a. So s minus a is positive. Okay. So e power minus infinity tending to 0. So 1 by a minus s times 0 minus 1. So that is equal 1 by s minus a. So where s is greater than a. Therefore Laplace of e power at is equal to 1 by s minus a. S is greater than a. Similarly, Laplace of e power minus at, that is equal to 1 by s plus a. Now replacing a by minus a. So minus of minus plus a. So s is greater than minus a here. Okay. Now the third one is third one Laplace transform of sin 80. Okay. Laplace transform of sin 80. So is equal to a by s square plus a square, where s is greater than modulus of a. This condition is s is greater than mod a. So that is s is greater than minus a and s is greater than plus a. Okay. Now from the definition, Laplace transform of sin 80 are sometimes we have to calculate. Sin 80 can be written as sin 80 is equal to e power 80 iat minus e power minus iat by 2i. Okay. Since e power I theta is equal cos theta plus I sin theta. Clear? E power minus I theta is equal cos theta minus I sin theta. So now subtracting both of them, so we get sin 2I sin theta is equal 2I sin theta is equal e power I theta minus e power minus I theta. So therefore sin theta is equal e power I theta minus e power minus I theta by 2f. So now replacing theta by at. So then we get this one. Now applying Laplace transform on both sides. So Laplace of sin at is equal Laplace of e power iat minus e power minus iat by 2i. Okay. Now 1 by, again here applying linearity property. So 1 by 2i is constant. Okay. So Laplace of e power iat minus Laplace of e power minus iat. Clear? Okay. So again applying Laplace of, from we known formula, Laplace of e power at is equal 1 by s minus a. So here a means t quotient, here a means ia. So using the above formula, Laplace of 1 by s minus ia minus 1 by s minus of minus ia. Clear? Here a means minus ia. Now simplifying this expression, 1 by s minus ia minus 1 by s plus ia. Now taking LCM, s minus ia times s plus ia. So s plus ia minus s plus ia. Clear? So s cancel, 1 by 2i times 2ai by s square a minus b times of a plus b, a square minus ia whole square. Clear? So 1 by 2i times 2ai by s square. So here I square a square. So I square is minus 1, a square plus a square. So here 2i cancel. So finally we get a by s square plus a square. Okay. So here Laplace of e power at is equal 1 by s minus, here a means ia. So here applying for this formula, s is greater than ia. Now here applying Laplace of e power at. So here condition is s is greater than minus ia. Clear? So from this formula, okay. So s is greater than a. So now we are applying this formula. So s is greater than ia, s is greater than minus ia. So s is greater than modulus of ia. Then s is greater than, so mod ia means modulus of I into mod a. So then s is greater than modulus of I means 1 into mod a. Then s is greater than mod a. So this is the condition. S is greater than modulus of a. So mod I means 1, because mod I can be written as 0 plus 1 times of I, that is equal to square root of the magnitude of complex number 0 square plus x plus yi. X means 0 square, x square plus square root of x square plus y square. So 1 square, that is equal square root of 1 means 1. So okay. So therefore Laplace of sin at is equal a by s square plus a square, where S is greater than modulus of A, absolute value of A. Okay. Now, next fourth one, we have to prove that Laplace of cos et. Similarly, so Laplace of cos et means here cos theta means cos theta. Cos theta means adding both of them, 2 cos theta is equal e power I theta